Welcome guys to another lesson, and in this lesson we are going to talk about extending Python. And the simplest way of extending Python is by writing our own functions. We can define these in the same file as the code that uses them, or we can create a new module and import the functions from there. We look at modules in this section now. Now we will create some functions and use them in the same file. In fact, we will mostly be using the interactive prompt for the examples in this for this section. The next step in creating new functionality in Python is to define our own classes and create objects from them. Again, it is common to create classes in modules, and we see how to do so in the next sections. The examples here are simple enough that you can just use a Python prompt. Python programmers frequently use documentation strings in their programs. Documentation strings are string literals that are not assigned to a variable and respect the indentation level at which they are defined. We use documentation strings to describe functions, classes, or modules. The help function, as I mentioned earlier, reads and presents documentation strings. So defining and using functions. Several types of functions are available in Python. And this section looks at the standard variety first, followed by a generator function, and then concludes with the slightly enigmatic Lambda function. So we define functions in Python using the def keyword, as shown here. Make that a little bit easier to read. And this is the form of a function. You define a function, have some parameters, and the function of the function block. Python functions always return a value. You can specify an explicit return value using the return keyword. Otherwise, Python returns none by default. If you find unexpected non-values appearing in your input, check that the function concerned has an explicit return statement in its body. We can give default values to parameters by following the name with an equals sign and the value. And we'll see an example of a generator function in the next section. So let's try to create a new function that takes several input parameters and returns a value. And the function that I'm going to show you is a mathematical equation of a straight line to return the corresponding y coordinate of for a given gradient, x coordinate, and constant. We then use the function to generate a set of coordinates for a line. So I'll just type in the code first, and I'll explain it after I've typed the code. Like I said, this is a small function, so we will just write it in the interpreter. Code typing is very silent work. course. Sorry about the mistyping. I just had to retype it again, and like I said, it's unfiltered. I'm going to make mistakes like lots of developers do. So now let's test our function. We have defined it, and we'll test it using some simple values that we can calculate in our head. So by calling the function with a gradient of 2, an x value of 4, and a constant of -3, should produce 5. It does. So let's try a more complex text of the function. And let's also check that the help function correctly recognizes the function. Gives us the doc strings and the documentation of the function, how it's supposed to work. So how does it work? In the first line in step 2, we created the function definition. We named it straight line and said it had 3 required parameters: gradient, x, and constant. These parameters correspond to the values used in the mathematical equation y equal mx plus c, where m is the gradient, the c is the constant. The second line is the documentation string that describes what the function is for and how it should be used. The third line is the function block code. It could be arbitrarily complex and several lines long, but in this case it's a one-liner and we are returning the results, so we prefix it with the keyword return. And note that the code line has to start at the same indentation level as the start of the documentation string, otherwise we will get an indentation error. We then tested the function with some simple values. Some mental arithmetic confirms that the return value of 5 does indeed include 2 times 4 minus 3, 8 minus 3. The function seems to work, at least for a simple case. We then use the function to generate a set of xy coordinate pairs using a for loop with a fixed value for the gradient 2 and the constant -3. By applying the loop variable as x, if we have some paper handy, we can try plotting the coordinates listed to confirm that they form a straight line. And finally, we use the help function to confirm that the documentation string was correctly detected and displayed. That was defining and using functions. Now let's talk about generator functions. And generator functions look exactly like standard functions, except that instead of using return to pass back a value, they use the keyword yield. In theory, they can use return in addition to yield, but only the yield expressions produce the generator behavior. The bit of Pythonic magic that makes generator functions special is that they act like a freeze frame camera. When a standard function reaches a return statement, it returns the value, and the function then throws away all of its internal data. The next time the function is called, everything starts off from scratch. The yield statement does something different. It returns a value just like return does, but it doesn't cause the function to throw away its data. Instead, everything is preserved. The next call of the function picks up from the yield statement, even if that's in the middle of a block or part of a loop. There can even be multiple yield statements in a single function. Because the yield statement can be inside a loop, it is possible to create a function that effectively returns an infinite series of results. So this example here, this example here returns an incremented series of odd numbers. And in this function, we first check that the start argument passed is an odd integer, and even integer divided by 2 has a 0 remainder, and if not, we force it to be the next highest odd integer by adding 1. We then create an infinite while loop. Normally this would be a very bad idea because our program would just block forever. However, because this is a generator function, we are using yield to return the value of start. So the function exits at this point, returning the value of start at this moment in time. The next time the function is called, execution starts right where we left off. So start is incremented by 2, and the loop goes around again, yielding the next odd number and exiting the function until the next time. Python ensures that generator functions become iterators so that we can use them in for loops. Like in this example, we use odds function just like a collection. Every time the loop goes around, it calls the generator function and receives the next odd value. We avoid an infinite loop by inserting the break test. So we never call odds beyond 7. So if we use odds a second time in the same program, it creates a brand new instance of the iterator and the sequence starts over. Just note that. So now that you understand how generator functions work, you may have realized that the generator expression introduced earlier in this chapter are effectively just anonymous generator functions. Generator expressions are effectively a disguised form of a generator function without a name. This provides a perfect segue to the final function type we will be learning about here. That's a lambda function. The term lambda comes from a form of mathematical calculus invented by Alonzo Church. The good news is that you don't need to know anything about the math to use lambda functions. The idea behind the lambda function is that it is an anonymous function block, usually very small, that we can insert into code that then calls the lambda function just like a normal function. Lambda functions are not things you will use often, but they are very handy when you would otherwise have to create a lot of small functions that are used only once. They are often used in GUI, graphical user interface applications, or network programming contexts, where the programming toolkit requires a function to call back with a result. A lambda function is defined like here shown on the foil. Let me make that a little bit readable. So that's the literal word lambda, followed by an optional comma-separated list of parameter names, colon, an arbitrary Python expression that usually uses the input parameters. Note that the expression does not have the word return in front of it. And some languages allow Lambda functions to be arbitrarily complex. However, Python limits you to a single expression. The expression can become quite complex, but in practice, it's better to create a standard function if that is the case, because it will be easier to read and debug if things go wrong. We can assign Lambda functions to variables, in which case those variables look exactly like standard Python function names. So let's show you example with the straight line example function re-implemented as a Lambda function. I'll just restart this. Excuse me. It's good to see. It's good that you can see me messing around. It produces the same result as we did earlier. So we will see Lambda functions popping up later in the course. Just remember that they are simply a concise way to express a short single expression function. So now also in this section, talk a little bit about defining and using classes and objects. Python supports object-oriented programming using a traditional class-based approach. Python classes support multiple inheritance and operator overloading, but not method overloading, as well as the usual mechanisms of encapsulation and message passing. Python classes do not directly implement data hiding, although some naming conventions are used to provide a thin layer of privacy for attributes and to suggest when attributes should not be used directly by clients. Class methods and data are supported, as well as the concepts of properties and slots. Classes have both a constructor, the new method, and an initializer, the init method, as shown on the foil, as well as a destructor mechanism, del, although the latter is not always guaranteed to be called. Classes act as namespaces for the methods and data defined therein. Objects are instances of classes. Instances can have their own attributes added after instantiation, although this is not normal practice. A class is defined using class keyword followed by the class name and a parenthesized list of superclasses, like in this example here. The class definition contains a set of class data and method definitions. A method definition has as its first parameter a reference to the calling instance, traditionally called self. So what we see here is it's a very simple class definition. The class name traditionally starts with an uppercase letter. In Python 3, the superclass is always object unless specifically stated otherwise. So the use of object as the superclass in the preceding example is actually redundant. The instance count data item is a class attribute because it does not appear inside of any of the class methods. The init Function is the initializer. Constructors are rarely used in Python unless inheriting from a built-in class. It sets the instance variable self.__value, increments the previously defined class variable instance_count, and then prints a message. The double underscores before value indicate that it is effectively private data and should not be used directly. The init method is called automatically by Python immediately after the object is constructed. The instance method, a method, modifies the instance attribute created in the init method. The str method is a special method used to return a formatted string so that instances passed to the print function, for example, will be printed in a meaningful way. The deconstructor del decrements the class variable instance count when the object is destroyed. So we can create an instance of the class like this first line here. This creates an instance in memory and then calls myClass.__init__ parenthesis with the new instance as self and 42 as value. Here. And we can call the a method using the dot notation like this. And this is translated to the more explicit invocation and results in the desired behavior whereby the value of the ___ value attribute is adjusted. And we can see the str method in action if we print the instances with the print method, and it will print out this message. We could also print the instance_count value before and after destroying an instance, like here. And this should show the count being incremented and then later decremented again. There may be a slight delay before the deconstructor is called during garbage collection, but it should only be a few moments. The init, the del, and the str methods are not the only special methods. Several of these exist, all signified by the use of double underscores. They are sometimes called dunder methods. Operator overloading is supported by a set of these special methods, including add, sub, mul, and div, and so on. Other methods provide for the implementation of Python protocols, such as iteration or context management. And we can override these methods in our own classes. We should never define our own dunder methods, otherwise future enhancement to Python could break our code. We can override methods in subclasses, and the new definitions can invoke the inherited version of the method by using the super function, like shown here. The call to super.init translates to a call to the init method of parent. Using super avoids problems, particularly with multiple inheritance, where a class could be inherited multiple times, and we usually don't want it to be initialized more than once. One thing to note is the use of super in Python 3 has been greatly simplified compared to its Python 2 form. The super line in Python 2 would look like super and in parentheses subclass, comma self, dot, __init__, and a value in parentheses, which is much less intuitive to use. And slots are memory saving device, and you invoke them by using the __slots__ special attribute and providing a list of the object attribute names. Often slots are a premature optimization, and we should use them only if we have a specific known need. Properties are another feature available for data attributes. They enable us to make an attribute read-only or even write-only by forcing access to be via a set of methods, even though the usual method syntax is not used. This is best seen by an example that we are going to create, a circle class with a radius attribute and area method. We want the radius value to always be positive, so we don't want clients changing it directly in case they pass a negative value. We also want area to look like a read-only data attribute, even though it is implemented as a method. We achieve both objectives by making radius and area properties. So we will create a simple circle class in our IDE that has only one attribute and two callable methods, set radius and area. Then we create a second class, circle2, which makes radius and area properties. And finally, we'll see how to use the properties, how the use of properties simplifies the use of class in client code. So let's just start to type in some code. So I will be typing for a while, and I will, if you don't want me to see type, just you can fast forward it where I explain the code. This usually creates some error. And then define a new class. just have to make sure I'm typing correctly. So let's save the code. Hopefully this will work. Otherwise we just have to debug it. And now let's go into our interpreter, and we should move into our directory where we created that file. Test circle is there, so let's start Python. Okay, it's importing. That means it's connecting. Let's create an instance. If I can type correctly. I'll explain in a minute what I'm doing. Testing it, the negative value. Value must be positive. Good. Let's create another instance of circle2 class. Good. So let's see what's going on here. I made some mistakes, but you just have to bear with me. So in the test circle py, we created two classes. The first class, circle1, achieved what we wanted to do by forcing the user to change the radius via radius value via the setRadius method. We did this by prefixing the attribute self.__radius, which is how Python makes things appear private. We then created the setRadius method that validated the supplied value before applying it and raised an error if a negative value was found. We also provided an area method so that the user could evaluate the area using the usual method calling technique. The second class, circle2, went about things rather differently. It used Python's property function feature to create an attribute called radius that was write-only. It also created the area method as a read-only attribute. This made the user code for circle2 much more intuitive, as we saw when we exercised the classes in the interpreter. The key lies in the property type function that we called. This code takes arguments, a set of functions for read, write, and delete, as well as a documentation string. The default value of each is none. In this case, we created the radius property with a non-read function, but with the now private __setRadius method as a write function. The other values were left at their default of none. The result was that radius could be accessed by the user as if it were a public data attribute when assigning a value, but under the covers, Python called the __setRadius method. Any attempt to read or delete the attribute would be ignored because the action gets routed to none. The area property is slightly different and uses a Python property decorator, @property, which is just a shortcut for creating a read-only property. This is a very common use of properties. So looking at the interactive session, we created circle1 instance and printed the area using the area method. We then tried to print the radius directly by accessing the __radius, but Python pretended that it had no such attribute because of the double underscore private setting and raised an attribute error. When we used the setRadius method, all was well, and printing the area a second time showed that the modification worked. Finally, we tried to set a negative radius, and as expected, the method raised a value error exception with the custom error message value must be positive. And so in the session using circle2, we can see how much simpler the code is. We simply evaluate the area property name to get the area, and we assign a value to the radius property name. When we try to assign a negative value, the method again raises a value error. Printing the radius directly again generates an attribute error, although this time it has a slightly different message. And properties require a small amount of extra effort on the programmer's part, but can greatly simplify the usage of the class. So this is the end of this section. So having seen how to extend Python capabilities using function and classes, and in the next section we are going to go through how to enclose this extension in modules and packages for reusability. So I will see you in the next module.